So the next speaker is Robert Layton, and I'd like to introduce him. He is a researcher at the Internet Commerce Security Lab at the University of Ballarat. And he's worked on projects and supervising students across all three of these areas. So that is internet, commerce, and security. And so he's been investigating cybercrime attribution using features within attacks to determine patterns and build machine learning models around those patterns. So he'll be talking today about using scikit-learn to help with cybercrime attribution. So thanks very much, Robert.
Thank you. Thanks for coming to my talk. I wear a number of different hats for this presentation. I'm a research fellow at the University of Ballarat in the Internet Commerce Security Laboratory, and we have industry partners Westpac and the Australian Federal Police and IBM. Basically, our goal is to disrupt cybercrime. The word disrupt is deliberately broad, and in many ways our research in the area is deliberately broad. I'm also a contributor to the scikit-learn library. I wouldn't say I'm a core contributor, but I try and do as much as I can. The scikit-learn library is pretty much a base dependency for all the research that I do. There's a number of positives to using this from a machine learning point of view that give us a sort of framework that easily allows us to develop new models, test them out, not have to write cross-validation code, and it gives us access to a lot of frameworks that are really useful. So there's three main chunks in my talk today. I'll be talking about the scikit-learn library for those that haven't heard of it or want to know a little bit more information. I'll be talking about how to contribute and some future directions we're hoping to go in. Also going to be talking a very small introduction to machine learning itself. Basically for those that aren't familiar with that, and finally give a summary of some of my research in cybercrime attribution. So it's an introductory talk in each of these three areas, so I hope that most people here are knowledgeable at two of the three areas and not all three, but so I hope everyone can get something out of it. So the scikit-learn library was originally a Google Summer of Code project in 2007. It was revived in 2010 and then turned into a community-driven project. We on GitHub, where most of our development happens. They're in the mailing list, of course. But basically, what separates a scikit-learn library from other machine learning libraries in Python is that we try to be very accessible. There's languages that do big data better, there's languages that do particular algorithms better, but from a personal point of view, I think scikit-learn has that good focus where we've got a large number of algorithms. They're all fairly well written, they're all really well documented, if you want to do sort of research in this area, I find this library is really good because in many regards what, say, machine learning research comes down to is we want to test out a big bunch of algorithms, and if we can do all that in the same framework, that really benefits moving the research along quickly. So the library itself it has supervised, unsupervised algorithms, which I'll get to the distinction a bit later. Has a large number of metrics, metrics in both the sense of the word, where evaluation metrics such as accuracy and F1 score are implemented, as well as distance metrics like cosine and Manhattan distances are also in there. The feature that I find most useful about it is the framework code, and there's a few mix-ins which give us access to sort of an abstract class, and from that abstract class we have things like cross-validation code that just performs duck typing on those models. And this is where I use the library in my research most. Is I have my models come off those mix-ins, and that allows me to use the evaluation codes within scikit-learn very easily. One of the advantages I find about Python is because you can code something up so quickly, the developer then has more time to document. And I think most libraries that are going to be talked about in this conference have very fantastic documentation. And I think this is a direct effect of the fact that you can code something very quickly in Python, and it means we have time to document it. And scikit-learn is no different. There's really fantastic documentation for, I'd probably say, about 90% of what's in there. If you're contributing features to the library, you have to write documentation or it won't get in. And as well as that, we also have a number of tutorials, both in the official docs and unofficial. And most of the main developers, except for myself, have blogs that regularly post on features or applications of scikit-learn. So as I said, we're on GitHub. We use Python. Python is used for speed in many cases. We have 88% test coverage, but this isn't adjusted for platform-specific code, which we have a little bit of. And if you're interested in contributing, just jump on our mailing list, introduce yourself. And this is especially important if you're proposing new features, because we are pretty strict about coding styles. So we're keyword compliant from a machine learning point of view, SVM, naive Bayes, hidden Markov models. We have a very large number of algorithms. It's not comprehensive in any regard, but we're getting closer. So for those that know what these words are, there's a very large chunk of algorithms, and as well as that, we have plenty of examples of usage, not only your sort of 101 introductory usage, but also more in-depth applications that are pretty standard, like topic clustering. So I'll just go over a couple of tutorials we have. The one in the official docs was originally for 1-hour tutorial, so there's a large amount of content in this tutorial, and it's now part of the documentation. I'm not sure it's in the last release, but it's definitely in dev. And this gives an introduction to machine learning, which is very accessible for anyone that hasn't done it in the past, and uses scikit-learn for all the code examples. Going through this tutorial, even if you have some machine learning knowledge, is a very useful exercise in covering the gaps and making sure you're aware of everything. There's lots of applications. So in here we have an eigenface extractor where we're able to sort of extract features from faces and use that for classification later. Another tutorial is astroML. I think a couple of our core developers are sort of Astro people, and they use, there's another library, astroML, which has a link down the bottom, and this library is based off scikit-learn. So if you're in that field, then this is a good library to have a look at. But they've developed a tutorial on using it for astronomy, and while you may not have a particular application in this area, this is a good tutorial to go through as well. Both tutorials there are really well written. As well as that, we have a large number of tutorials at that page. Some of them are quite short and very specific, and some of them are quite long from tutorial sessions at other conferences. And as well as that, some of the tutorials itself are hosted on GitHub and allow contributors, and they're getting quite active in particularly one of the tutorials. So what is machine learning? And the disclaimer down the bottom is very important. Magic hand waving, some of the stuff here is not technically accurate, but it's good enough. So machine learning basically is trying to find information from data, and there's a large number of applications. Classification is one most people are familiar with. Is this particular email spam or not? Facial recognition is another one. Image segmentation is another one, and but what does the actual data look like? And there's many different ways to represent data. The model that scikit-learn uses is basically an XY model. So X is a 2D array of feature values, and each row in this matrix is one thing, and each column is one attribute of that thing. The example I've got up here is from a famous data set of iris plants, and the first row corresponds to one plant, the second row corresponds to another plant. The first column, I think, is the length of the petals on that plant, and the second column is the width, or I might have those around the other way. So we can say that, for instance, the width of the petal of the first plant is 3.5 centimetres, or equivalent. So this is our X matrix, and this describes our things. The Y array is basically what type of thing is it. And in a classification task, this might be 0 if the email is not spam, and 1 if it is spam. And basically, the length of this Y array has to be the same as the number of rows in the X matrix. And basically, Xi are the features for the object, and Yi tells us what that object is. So this is the data model that that scikit-learn uses. So the supervised is unsupervised distinction. If ahead of time we know what Y is, like we know what sort of things we're looking for, then it's called a supervised learning task. And we use algorithms like support vector machines or naive Bayes. We build a model around those things that we do know, so that we can predict what the type is of things that we don't know. So we have a corpus of email. We build a model based on whether it's spam or not. We use that model to look at new emails and determine whether those new emails are spam or not. If ahead of time we don't know what Y is, it's an unsupervised learning problem. And one of the most common examples of this is topic clustering. You know, we have this large collection of documents, and we want to know, what sort of topics are in that corpus. So what we do is we perform clustering and put documents that are very similar to each other together, and then those groups that come out from that clustering process give us not a topic, but it gives us a group, and then we can manually examine that group and see what sort of topic all those things are. And if we do this well, this can be a very good exploratory analysis on data. It tells us what's in data without knowing beforehand. So with classification, as I said, we have a large number of dots there. The colour is what we knew beforehand, and these are plotted against two different attribute values. So the dots are what we know beforehand, and the background colour is what we would predict a new object to be. So if we had a new object with values 8 and 2, it would appear in the blue area, and we would predict that it's that object. And it's very easy to do. Line 1 is basic import, line 2 and 3 is basically extracting the data. This could be pre-computed beforehand or computed some other way. Line 4, we develop a model. So pretty much we just instantiate it. Line 5 is we fit that model to the data that we know of. And this sets internal attributes and parameters. And then line 6 is we have new data that we don't know. We call the predict function on our model, and it tells us what at least the model thinks it is. So in 6 lines of code, we develop that. Not the graph, but the model for it. So one of the big benefits is that of the scikit-learn is that line 4 can be swapped out and replaced with other algorithms, and this whole process generally still works. And we have a large number of algorithms, and as you can see, with sort of those background colours, they all work in different ways. The meaning behind how they work, why they've chosen those decision boundaries, is part of the machine learning literature, and something, if you're interested, to talk to me about it later. So we have a large number of algorithms. They're all good in some ways, bad in other ways, fast, slow, scalable, not. So this is the case where with that Y value, we know what it is beforehand, and it's also distinct classes. You know, it's this type of plant or it's this type of plant, it's spam or it's not. If we don't have that sort of discrete knowledge, we have a similar problem called regression. Now regression is, you know, it's not spam or not, but it might be what is the height of someone given, you know, their weight and gender. You know, how can we predict their height from that? And their height is a continuous variable. It could be anything from, you know, one value to another, and it could be, you know, at any point in between there. And this sort of problem is called regression. Pretty much we can just have a look at how different models, so in this figure we have different dots, which are our ground truth. So this is what we knew beforehand, and our lines are trying to fit a model to that ground truth to try and predict new values. And you know, this is a tricky problem in many cases. And to have a look at the regression code, nothing changed. Line 4 is a different model, but that's it. Line 1's a different import. Line 4 is a different model, but as well, you know, but that framework is still the same. And this is something we can rely on for new models in the library. Now, for unsupervised learning, we have a whole bunch of dots there, and we don't know, they're all black, you know, we don't know beforehand what any of them are. And what this data set is images of digits, so someone's drawn a 1 or a 2 or a 3. It's been represented using its intensity values. Then we've plotted against these 2 dimensions, and we've performed some clustering to try and find different clusters. Now, the background color is what it's going to be predicted as, and as I've said, you know, down the bottom, ignoring some complex philosophical discussions about clusters and classes, this is about 60% accurate. And more hand waving, the points that are going to be clustered together are generally going to be the same number, about 60% of the time. And this is without, you know, any prior knowledge except for the number of clusters in this case. Now the code for clustering is pretty much the same, except we don't worry about why because we don't know it. And line 5 is we just extract the labels themselves from the model rather than try and predict new data. Generally with clustering it's exploratory. You know, we have our one data source and we try and put classes onto that data source rather than take new data. And we have a whole bunch of different algorithms. One of the key issues in the unsupervised field is that of parameters. The last column here, the DB scan algorithm, sort of appears to do clustering very, very, very well. But this was fiddly with the parameters. You know, you had to choose parameters beforehand that gave us this rather than just some magic algorithm which does what we want all the time. So why use scikit-learn? Clear, easy to use APIs. It's very fast in most use cases. We make good use of Python, you know, as was introduced earlier, you know, which gives us Python-like code that runs really fast. We have good parallelization. It's easy to use. I wouldn't say it's the most scalable thing, but it's incredibly easy to use, and it's well integrated within scikit-learn. Lots of utility functions, as I said. You know, I don't, for my research, I don't build models that are already part of the scikit-learn library. I build new models, but I can just use the utility functions within scikit-learn very easily. And these are some complex utility functions as well. Great documentation and getting better. There's a great community as well, and it's growing as well. So where's the scikit-learn library going in the future? We recently performed a survey, put in a survey on our homepage and asked people to respond. 57% of scikit-learn users that completed the survey are academic, and 36% were industry. And what people want to see in neural networks and deep learning, which is not really surprising, this is sort of where the field's going. People who are familiar with machine learning in, say, the 80s would have seen neural networks back then and they didn't do very well, but there's been some really big breakthroughs in the field in the last few years, and neural networks are now where all the latest cutting-edge results are coming from. Structured prediction, Python 3 support. Now we have Python 3 support, but it needs work. So if you're really good with Python 3, let us know. And sparse matrix coverage increased. We have many algorithms that support sparse matrices from the SciPy library, but not all of them do. Now, I'll skip through this, but if you're interested in contributing, jump on the mailing list or let me know, or both. There's a sprint, and if you're interested in helping fund that, just again let me know and I'll point in the direction of funding. So now, more hand waving inside, but now I'll get to the cybercrime attribution part of my talk, and I don't have much time. So basically, my main issue that I'm trying to resolve in my research is we can't directly determine who is performing a cyber attack. What people do is they set up behind proxies or use Tor or all these bunch of other technologies that are very, very good at preserving this. So what we want to do is we want to find other ways to link attacks to the people. And I apologise I don't have too much time to go into the details, but what we basically do is we extract text features from documents, we cluster them, we do this with a bunch of different parameters, and then we get clusters out where we can say that all attacks within the same cluster are from the same person. This is a diagram of one of my latest algorithms. And what this allows us to do, when we apply it to phishing websites, this sort of attack pattern by itself is very random. But once we extract it into groups, we're able to do a lot more prediction around what those groups are. Those that know their phishing history would know that in October 2009, a particular group called Rockfish had a large chunk of their infrastructure taken down. Now, independent correlation shows that the light blue group is Rockfish, which were very prolific in 2008, 2009, and then at October 2009, you can see that they pretty much died. And this correlates with what we know externally. So we're able to here we're able to track different phishing groups without knowing beforehand what those groups are, and this gives us a lot of intelligence. So that's my talk. So yeah, I sort of went over a lot of material, 3 different areas: scikit-learn, machine learning, and cybercrime attribution. So if you have any questions on any of those, just let me know. Thank you.
Yeah, thanks to Robert for a very good talk, and thanks for your work on scikit-learn. Questions? I'll come back to you. Okay.
If you could very quickly, with that attribution of phishing websites, what are some of the features that you use for that clustering?
Okay, so for a topic clustering, where we want to know what the topic of a document is, we extract the words, get rid of some of the words that we know aren't useful, and if it's a sports document, it's going to have football or ball in it a lot more than common usage, and we put those ones together. For authorship, we look at the characters instead. The frequency of character engrams or subsequences of characters is different for each particular author. And what we can do is we can extract those character subsequences out, model the overall usage, and then use that to model their authorship style. And then we compare these profiles of authorship to each other. The top, well, the sort of the blue, green, yellow, green models are different types of authorship models here, and then the rest of it's pretty much an ensembling approach. Yeah, so there's a bunch of different ways to actually do the modeling, but those character engrams are very effective. Yeah.
My question is about if you know some way of providing the models as a service using scikit in a way of where you can online provide feedback to keep training the model and control the overfitting that you can have when you provide new data.
Sorry, I didn't quite get that.
So basically, once you train your model, you can then provide as a service, right? So you can have online data coming that you can retrain your model one another time.
Okay, yeah.
And that can provide you some overfitting that you should avoid to keep the accuracy of the model pretty high. And my question is if you know if in scikit-learn there is something to provide that model as a service where you can give this feedback of data and keep it trained.
Yeah. So the problem you talked about there is called online learning, where we have a model and we update it with new information. I'm not actually sure whether we have any in there at the moment, but I have heard talk about it on the mailing list. I'm more of an unsupervised clustering guy, so I'll focus on that. But I believe it is something that's being looked into. Yeah.
There's a question here.
It's not really a Python question, but for the example you gave with phishing, how do you pick your number of clusters?
Yep. This algorithm here, for anyone that knows cluster analysis is going to sort of scoff at what I'm about to say, but this algorithm here is an automated method for choosing the number of clusters. With any unsupervised approach, there's always some interpretation in the results, and it's very difficult to get rid of that. What I've done here is, from this top step, we get a whole bunch of different clusterings, and basically we use a framework called EAC that remaps those. And what the purpose of this is we take clusters which may not be that separated initially. We do EAC, which makes those differences a lot bigger. It makes it easier for us to automatically select the middle point to separate two things out. It's not perfect. I think this is about, the hand waving 70% accurate. But I mean, I found that this works quite well, and for the phishing data set, we had about 99% purity with expert analysis of the same data set.
We have time for, I think, one more question. Nathan?
The good news is you just answered my question. But quickly, so you're using Kmeans, right? Could you have used another clustering algorithm that had some magic about picking the clusters for you? Like, I know there's some clustering algorithms there that you showed before that you could just use without specifying K.
Yep. So the Kmeans used here is done with random K values, and it's that random K value is the first part into the EAC algorithm. Then EAC does the magic on those different clusterings and combines them. So I'm happy to talk to you offline in more detail, but basically at the top it's random, how many clusters, and then at the bottom hopefully it's not. Yeah.
So thanks again, Robert.
Thank you.
We'd like to offer you a bag of coffee and a mug for it. So
fantastic.
Thank you very much.
Thank you.
The